Okay. There should be a way. Uh, okay. Okay, so as Sailik said, Goleang had to be at a different meeting that was scheduled at the same exact time. And so Sailik went and did a separate presentation to him, and he will be joining us, I think, at 11 o'clock or just before that, so that he will still be there for the committee Q&A. So that's at least the plan. That leaves, I guess, Dijang, Tiffany, and myself as the committee members. Okay, so since it's coming on 10:03, let's get started. Today, Sailik is going to be defending his PhD dissertation titled The What, When, and How of Strategic Movement in Adversarial Settings, a Syncretic View of AI and Security. So before he gets started, it's normally what I do is try to give like a thumbnail sketch of their time in my lab. So I'd like to say a few words about Sailik, if you would indulge me. So Sailik received his bachelor's in computer science from Jadavpur University. And after working for 2 years in Amazon, India, he joined ASU PhD program in 2015. During his time at ASU, he made important research contributions in multiple areas and published many rigorously refereed papers that have up until now received around 280 citations. Sailik also is the recipient of the prestigious IBM PhD fellowship during 2018-20, and he interned at Amazon AI for 2 years, and pending completion of this successful completion of this defense, he'll be joining Amazon AI as a research scientist. As we shall see today, for his thesis, Sailik has, at least I believe, done impressive work in the area of AI and security. That's, however, not the only area he worked in. One distinctive characteristic of Sailik is his sheer range. He is able to pick up things in multiple seemingly disconnected areas at a rather envious rate. It's no wonder that in addition to cybersecurity, Sailik has refereed papers on topics including heuristics for automated planning, human-aware planning and decision support, trust and explainable allocation in AI, game theoretic AI and multi-agent reinforcement learning, bias and inexplicable failure modes in machine learning, and finally, natural language processing. In fact, he actually will be joining Amazon AI natural language processing group as a research scientist. This certainly is an impressive proof of his range, even after accounting for the fact that NLP these days is but application of deep learning to sequence data, and there's really not more than that there. But still, it's very impressive that he has been able to do these many different things. Sailik's breadth is coupled with a surprisingly generous and mature ability to mentor and collaborate with many people, including junior students. He co-authored papers spanning a range of topics with Niharika, Alberto, Zara, Sachin, Sharath, Tathagata, Lydia, and Satyagautam just in my group. And also Ankur and Kaustav and Adam Dupé and Jung and several others outside of our group, including some folks from IBM that he has written papers with. Sailik has both a sense for elegant theory and a knack for effortless coding. His collaborators knew that he can whip up systems under time pressure and sometimes take advantage of that. So if you don't do anything last minute, Sailik will somehow make the system happen. As early as his second year in his PhD here, he became the de facto web chair for the 2016 International Joint Conference on Artificial Intelligence that I was program chairing. And he basically ran the entire web system there for that conference. Sailik has been a lively presence in the lab and our group. His ability to pick up things quickly meant that he could provide constructive critiques on any topic being discussed or presented. Often he'll be able to convert a bout of armchair philosophizing in the lab into a concrete contribution and paper. His most recent work on explicable misclassification is a great case in point. I have already mentioned about his generous mentoring, and in addition to that, when something needed to be done in the group for research projects or funding or infrastructure, Sailik is the first one to step up. He gave hour-long presentations to NASA and ONR program managers and helped in writing successful grant proposals that are not directly related to his thesis research. In fact, the last 2 years, I wasn't even paying him. IBM was paying him, and yet, as a fellow, and yet he was doing all this stuff. For a while, in the beginning, he also distinguished himself for his competitive eating. I understand that in the lab, he was called Giganter or Giganter, and there is even a group of followers of Giganter who are into, following his eating exploits. This unfortunately, however, fell by the wayside when Srijita came in and enforced a strict dieting regimen. One of the most incongruous sights in the lab for a while was seeing Sailik eating fruits and salads for lunch. Sailik certainly has his share of luck. As an example, he just had 2 additional papers accepted just this last week, right in the time for his defense, with the last one coming yesterday. There is also, of course, his luck in persuading Srijita to take him on. But then again, as someone said, luck is but preparation meeting opportunity. They say a PhD is someone who knows something about everything and everything about something. Sailik certainly fits this description to some extent. I'll certainly miss having a resident polymath in the lab, even if it often entailed me scrambling to read up the background on whatever new area he decided to make inroads into. All in all, it's been a privilege having Sailik around in my lab, and I look forward to his continuous exploits post-PhD if he were to complete this defense successfully. Okay, so that's all I wanted to give as by means of introduction. Now Sailik can take away and present his defense.
Thank you, Rao, for all the generous comments there. I will obviously thank you and a lot of the other collaborators I have had the fortune of working with towards the end of the presentation. But for now, I'll just start off with my defense presentation. The committee members for today is Dr. Subbarao Kambhampati, who's also the chair, Dr. Tiffany Bao, Dr. Dijan Huang, and Dr. Guliang Shue. So the most widespread or popular notion in the security of static systems or static software is this idea of reactive security, where the attackers or even researchers explore a system, find new vulnerabilities, and then find patches that can actually fix or stop these vulnerabilities from being exploited. This is not only true for the software domain, but is also something of a trend that we have seen in the more recent area of machine learning security and power network security. An opposing notion, or rather a complementing notion for defense, is this idea of proactive defense and moving target defense in particular. So the idea here is that instead of having a single configuration of the system, you have multiple configurations of the system, and you keep switching between them with some particular strategy. And the idea is that the defender, when they seek to attack a system, not knowing which system they're attacking, they might not actually succeed. From the looks of it, it should be very simple to see that this idea of moving target defense is surely going to be at least as effective, if not more, than any reactive security mechanism. Because not only can you harden each of your system configurations using the existing notions of security in static or reactive security, but you could also, on top of it, use a defense in depth solution such as moving target defense. And so basically the questions should be, why not always use moving target defense? And so we take a critical view of this question in this thesis, and we ask that in which cases are you actually not so well off using moving target defense? And if you are using moving target defense, are there downsides to it? And if there are downsides to it, can we address those challenges and fix the problems? In particular, we look at the notion of switching costs. So basically, when you have multiple systems, switching between these systems will incur an extra cost. You might have asymmetric performance impacts for each of these individual systems. And sometimes using a moving target defense might not really be a good strategy because all of your configurations might be vulnerable to a single attack, at which point, what's the point of spending the effort in making up all these configurations? So in this thesis, I will kind of break down moving target defense into three important questions. One is, how do we move? Which is basically finding a strategy for movement. To address this answer, we will look at a game theoretic modeling of the problem where a defender will have a set of systems and an attacker will have a set of attacks, and the attacker will try to select an attack, and the defender, by just moving, will try to evade the attacker's attack. And this is something what we will call as AI for MTD. In the next part, we will look at MTD for all. Once you have learned how to make these moving target defenses effective, can you use all this knowledge or theoretical insights that you developed into making this problem, making this defense effective in new or novel settings? And we will use it for cyber deception, power networks, and deep neural nets. At the very end, I will spend a small amount of time talking about how we can think about, in a formal way, about the problem of when to move. Now, the agenda for this talk for my committee members and people who had attended the proposal, the papers that are highlighted in red are new papers that have happened after the proposal, and the papers highlighted in blue is something that I already presented at the proposal, but I'll also go over it during the defense so that people have a sense of where this is going. And in this regard, I will space out the works in the setting AI for MTD as inferring movement strategies, where you are given a model and you're inferring the best strategy for movement, or learning movement strategies when you don't have a model of the world. And in the section for using MTD in novel applications, we will talk about using the notion of MTD as a defense in neural networks against adversarial attacks, in power networks, and in cyber deception. Before I get started, I wanted to give you all a brief primer of game theory and the terms that I will be using throughout the presentation. For the entire presentation, I'll be talking about two-player games, which basically means, in my case, a defender and an attacker. I will talk about pure strategies, which also means the actions of players. So if this player was D, then the two pure strategies would be A1 and A2. When I say mixed strategy, I mean a probability distribution over the pure strategy. So if the defender chose to play A1 with a probability of 0.6 and A2 with a probability of 0.4, then that would constitute a mixed strategy. Now, I also wanted to give you an idea that the settings in cybersecurity is not a strict zero-sum game. Rather, it is a general sum setting, because an attacker might not often care about what is the performance impact that a defender is having, unless obviously it's only considering attacks such as DOS attacks or denial of service attacks and things like those. An attacker might have bragging rights on attacker forums for having exploited a vulnerability, and that the defender would probably not account for, and it would only care about the impact on its system. And henceforth, it's not easy to model all these cybersec games just as a zero-sum game that we see in chess or Go and stuff like those. In these games, I will mostly talk about Stackelberg equilibrium, which means that we have a leader-follower setting, which means that one of the players gets to play first, and the other player has the idea or knowledge about the other player's strategy. For example, if we talk about the Nash equilibrium of this game, then you will see that this is a Nash equilibria because none of the players can deviate away from this set of actions and gain anything. On the other hand, if you consider the Stackelberg equilibria, the defender would choose to play a 2 such that the other player can also play B2, and they both get a higher reward than they would have got for the Nash equilibria. And so this concept will keep reoccurring throughout the presentation. And it's just something to keep in mind that it is distinct from Nash because one player has to ideally play first, and the other player might gain the knowledge about the first player's strategy. And For the rest of the presentation, I will only be talking about normal form games, which look like this, as opposed to extensive form games, which expands the game tree. And as we go through the presentation, in some of the cases, I will introduce the notion of stochastic games. Before starting, I wanted to say that I will only be able to talk about a subset of works and not all due to interest of time. And I will start with the AMAS work. Now, to start with the AMAS work, I also wanted to point out that the AMAS work is a model-based strategy inference. So our expectation will be that there is some way we can get the model of the world and then use that to find good movement strategies. In one of the works that I will discuss later, we will discuss this notion of model-free strategy learning, where the model of the world can't be provided to us or is difficult to obtain. And in those cases, how can we find movement strategies? As Rao often says, that the robot's prayer to the human should be, human, grant me the serenity to accept the things I cannot learn, data to learn the things I can, and wisdom to know the difference. And so we will see that throughout the presentation, and I'll make distinctions for each of the individual works that I will present as we go. So in the AMAS work, which is there in chapter 3 of my thesis dissertation, we try to first model the moving target defense problem as a defender-attacker game. And in this case, this is an example that I'll use throughout. The defender has two pure strategies. That is, it can either choose to deploy a web application service using PHP and MySQL, or deploy the same web application service with the same functionalities using Python and PostgreSQL. And we will use the notation X, vector X, to denote the probability with which the defender selects this and the probability with the defender selects this as X2. Now, by conventional wisdom, the most popular strategy in these settings in cybersecurity has been the use of uniform random strategy, which says that pick each of these configurations with equal probability. A downside to such a setting is that you might choose less secure configurations with equal probability, you might choose less performant configurations with equal probability, and you even might incur high switching costs because you choose to switch between configurations that have high cost. So to address this, we will model it as a game. Now, to model it as a game, we also need to have a threat model or an attack model for the attacker. And in our case, we first model the attack actions that an attacker might have. And to find these attack actions, we mine the National Vulnerability Database and find common vulnerabilities and exposures. And with each CV, there's a list of technologies that it can actually attack, and also an expertise level required to use these, which is provided. And we will leverage that information. Now, in cybersecurity, modeling an attacker as a single attacker is kind of too naive, because oftentimes an attacker against your system might have different sorts of capabilities. It could be a script kiddie who just picks up vulnerabilities on the web and just uses it, versus it could be something like a nation state, which is an entire government funding an attack organization to bring down a system. And each of these different kinds of attackers have different sorts of expertise and a different set of technologies which they can exploit. And we use these expertise and technologies for each of the attacker type that we let you define in our game and pair them up with the CVEs to actually select a subset of attacks automatically that each of the attacker types can use. Now, once we have done that for each attacker type theta, we can use a vector Q to denote the strategy with which the attacker picks each of the attack actions in the game. So basically now we have a normal form game in which the defender has defense or configuration deployment actions, and the attacker has exploit actions that it can use against your system. Now, we obviously impose a normal reward structure, conventional reward structure imposed by conventional wisdom, where we say that if an attacker can actually exploit a configuration that you have deployed, then the attacker gets some positive reward, the defender gets some negative reward, and so on and so forth. But to get the actual values for this game, we leverage something which is known as the Common Vulnerability Scoring Service, which for each of the exploits that the attacker has, provides an impact score and the difficulty of exploiting or using that exploit against a system. And there is also a base score which combines both of this. And for the defender, we only care about the impact score that the particular exploit has on the system. For the attacker, we combine both because, for example, an attack which requires much more skill sets to exploit will have a higher cost for the attacker than for the defender would need to account for. Now, having done this, what we want to do is we want to maximize the expected reward of the defender. So the reward of the defender here is denoted by RDA theta AIC, which means that what is the reward of the defender if the attacker chose to use action A, the defender chose to deploy configuration C, and you are facing the attacker type theta AI. And basically this is just an expected value computation, which says the probability of you deploying configuration C, probability of the attacker choosing A, probability of the attacker type being theta, and then summing it over all of those. So this is just an expected value calculation for the defender's reward, which we are trying to maximize. Now, I also did say that for the Stackelberg equilibrium setting, we assume that the attacker will eventually get to know the defender's strategy. And knowing this, they will try to find a strategy that will get them the highest reward. So in this small part of the optimization problem, you will see that the attacker uses the values of the defender's strategy in trying to come up with their own strategy. Again, due to interest of time, I won't be able to go into a lot of the details of the optimization problem, but here are a few references that you can take a look to understand this. Now, one of the problems we addressed in this chapter was the case that even if you use this optimization problem to find a Stackelberg equilibrium, you are not guaranteed to get switching strategies that discuss the cost of switching or incorporate the cost of switching. So basically, moving between databases can be much more costlier than just changing code bases or changing the virtual machine you're pointing your requests to. And these things need to be accounted for in coming up with a strategy. And for this purpose, what we do is we incorporate an expected cost, which means the cost, if the cost for switching from configuration I to J is denoted as Kij, and you are in I with probability Xi, and you're switching to J with probability Xj, then in these cases, you will basically incur expected cost of this value, and you can sum that up over all possible switches and add it as a negative function. The only problem is that this adds a bilinear term to an already quadratic objective and makes the optimization problem much hard. And to approximate this, we use a popular technique in mathematical optimization that enables approximate variable and puts in constraints that upper and lower bounds this approximate variable to come with this strategy. Now, after all that math, what are we really getting out of all this? So the idea is that if, let's say, you were to have a system which could be deployed in 4 possible configurations, and there was a set of switching cost for switching from one configuration to another, and there was a set of attacker types that had technologies they could exploit and expertise in these technologies that they could use to decide their attack actions. Then if you model this as a game and solved using the mathematical optimization, what you would land up is with a final strategy. So this means after every time period T, the defender should switch between so let's start with URS, which is the uniform random strategy. The defender should switch to either of these configurations with probability 0.25. Now, if you use the formulated game and find a strategy, then you will see that we are saying that switch only between configurations 3 and 4 with probability 0.5 and 0.5. So one advantage to this is clearly that the expected defender reward in this case is better than if you use something like a uniform random strategy. And that's because of the modeling that you did in this domain. The second thing is that often developing all 4 code bases and 4 code configurations is not an easy task in cybersecurity or even software settings. And what BSG lets you do is prune out certain configurations that neither contribute to your security nor to your performance. Now, in this chapter, we discuss a lot of other results, which obviously I won't have much more time to go into, but a pragmatic problem that I wanted to touch over is finding vulnerabilities. So in most softwares, if you have multiple vulnerabilities, you decide on a limited dev effort to prioritize which vulnerabilities to fix. We show that this problem becomes harder in a moving target defense setting. And and henceforth, we suggest a very first step towards solving this problem, but again, a lot of exciting future directions in that regard. Now, having given an overview of the mathematical techniques that we'll be using through to find the Stackelberg equilibrium in such settings, I will not delve into the mathematical details for the rest of the talk. And what I will try to do is give you an overview and flavor of the different problems we solve and the different techniques that can be used in each of these settings as I go forward. So in GameSec, we look at the problem of multi-stage attacks. Basically, we say that when an attacker enters your system, they enter through a public interface and then find routes throughout your system to reach a final destination goal. And what the defender can do in such settings is essentially place intrusion detection systems at different points in the network to detect for the different vulnerabilities that the attacker might exploit. Now, a problem in these settings is that if you place all detection systems throughout the network, then you can have impacts on your bandwidth, impacts on your CPU resource utilization, and henceforth you have to do it in a clever way. And the idea of doing it in a clever way is to use moving target defense. Because if you only chose to place a subset of intrusion detection systems and you chose that to be static, then the attacker over time will eventually figure out where they are placed and just evade it. So that doesn't help you at all. And henceforth, you should use MTD in mixing up how you do the detection. Now, a problem to formulate this kind of a setting in the normal form game that I described a while back is that first, either if you have to account for all parts of the attacker, which might be like this, or have loops within them, which goes back, comes back, and then goes here, or completely different paths, then you would ideally have infinite attacker strategies or attacker PO strategies, which would make it very difficult for you to even solve a strategy in this game. The second option you could assume is that you can let the attacker attack only certain points in the system, but choose that they are much more powerful into attacking even the most deepest point in your network. And this is also sort of unrealistic, but this is an assumption that we make in one of our previous works. And to address both of these problems, a nice way to model this problem is using a Markov game. Using a Markov game provides us with this added benefit that due to the transition functions that are there in the Markov game, we can actually say that an attack doesn't always have to be successful, or a detection mechanism doesn't always have to be successful. I will get into a little bit more of these details as I go through this presentation. So first, let's describe a little formally what a Markov game would generally mean. A Markov game would mean that your system can be in certain states. The different players can have different sets of actions. And there's a transition probability which guides that if you're in this state and both of these players play an action from their respective action sets, then you will land up in a different state or even in the same state with a particular probability. Then there is a utility function for each of the players, which says that if you were in this state and you played something, say AI, and your opponent played A2 and or another action, what is the utility value that you're going to get out of this? And then there's a discount factor, which considers with what weight are you weighing your future rewards. And this could be different for both the players, but here we'll use the same just for being making this simplistic. Now the question is, it's all good that we have a formal model of the Markov game, but the question is, how do we obtain this? We were talking about some cybersecurity setting where we have to deal with attacks and defenses, and how are we going to obtain these Markov games exactly? And so the idea is based on some previous work already in cybersecurity, which transforms a network setting into something known as an attack graph. And we use this attack graph to formulate the Markov game. So now let's see how we are going to do that. So states of the attack graph in which we have certain privileges associated with the attacker become states of our Markov game. The attack actions of the attacker become the attack actions of the attacker player And the IDS actions which monitor for these attacks become the defense actions for the defender. Then we have the transition probabilities, which can be modeled as, for example, in this setting, if you're monitoring for a vulnerability or an exploit on the web service is based on a neural network, and you have a 95% chance of being successful in detecting it, then if you deployed the monitoring system and the attacker exploited, then with 0.95 probability, you would remain in the same state because the attacker won't be able to move to the next state. Otherwise, with 5%, when you can't detect the attack, the attacker can move to the next state. And so we model these kind of internal variables of the different IDS systems or even attacks, if the attacks can be successful with certain probabilities, into this Markov game. Then there's this part of reward modeling, which is very similar to the work I described earlier. But in this case, you have to define reward sort of metrics for each state of the Markov game. And basically what you're trying to incorporate here is that what is the impact on the defender, what is the gain for the attacker, and also what is the performance impact that the defender has. And we run some sort of mainnet simulations to figure out these values for the performance. Obviously, a lot of the details are there in the thesis, but again, I won't be going into all those here due to interest of time. So now you have the Markov game. You have found the states, actions, transitions, rewards. And so the question is, what do you do with this? And so the answer to that is you find a strategy in this Markov game that can help you with your IDS placement. And it becomes a little more difficult in the case of Markov games as opposed to in the case of Markov decision processes, which is for a single agent where you just compute the max of the Q values. In this case, if you want to calculate the value and the policies for both of the players, then you will actually have to solve an optimization problem similar to the thing we discussed in the previous chapter to find the value and probability and the policy. And so we do this, but we consider two different threat models. In one in which the attacker has no idea about the defender's placement strategy, and one in which the attacker has an idea about the defender's placement strategy. One neat thing that we prove in this work is that all the Stackelberg, strong Stackelberg equilibria that we can find in this Markov game due to a particular restriction imposed on the defender strategy set is a Nash equilibria, and hence both of them always give you the same reward. On the other hand, these strategies outperform min-max, where you assume a zero-sum case where the defender doesn't really care about performance but only impacts, shown in the green, and is much better than the uniform random strategy, which places IDS systems or doesn't place them with all equal probabilities. So how does this actually look in the setting, in a cyber setting? So the idea here is that what this would give you is a strategy for S1 to deploy a monitoring, to deploy an IDS or a monitoring service to detect LDAP vulnerabilities with 90% probability and not deploy anything with 10% probabilities. So we see this interesting thing where states which are not close to a critical state in your network can have some non-zero probability for you not monitoring at certain points in time. But as you come closer towards the more critical states in the network, then it will always tell you to monitor such things. And this kind of supports some of the conventional wisdom in network security with a formal grounding. We also run some experiments on a simulated cloud scenario where we have VMs that use the configurations of the Western region cybersecurity defense competitions. And we replay the attacks that we saw in the competition and use an SDN to deploy an MTD-based IDS. A lot of the details for this work is provided in the thesis, but I just wanted to say that some of this can also be actually used in realistic scenarios. Now, this work, both of the previous works talked about the case where you could form a model using a lot of the data that you had available. And a natural question to ask is, what happens when this is not? To the committee members, this is also something, this is the work that I had promised during my proposal that I would do for my defense. And this tries to address the problem that, let's say for this Markov game, you can't really obtain values for all the variables or for the normal form game, you can't obtain the rewards, and in this case, the rewards and transitions. And so a naive idea is that, okay, why don't we interact? If interaction is possible, why don't we interact with the cyber system and then just use some form of multi-agent reinforcement learning? That way I get to say on my CV that I've done multi-agent reinforcement learning and gain some bragging rights. But as it turns out, when I promised this work, I didn't realize that this could evolve into a monster of its own. Now, one reason for this evolution is that in the first work that I was presenting, I pointed out that there might be different attacker types in a cyber setting. And you need to account for these different types. And there might be uncertainty with what probability these attacker types are going to attack your system. And if you choose to do this, then the problem of multi-agent reinforcement learning moves into imperfect or incomplete information settings, which is a monster of its own in terms of scalability issues. And so to address these challenges, I do three things in this work, which is I propose a new game model, which can model the uncertainty over attacker types, but is also scalable, that can be applied to at least small and medium scale real world settings. The second case is I define a notion of Stackelberg equilibria in these games, and then propose a new multi-agent reinforcement learning approach to learn this equilibrium strategy. So in the first part, what I do is, and I wanted to point out to Dr. Bao as well, who already has work on POSGs, which is partially ordered stochastic games. So this is the most general model to kind of model imperfect or incomplete information in Markov game-like scenarios. If you tighten it and make certain assumptions, you could come down to Markov games with imperfect informations, which consider a series of Bayesian games and doesn't really assume the Markovian property, or the Bayesian Markov games, which talks about the belief states, which is what does the defender believe the attacker knows about the defender, and these kind of things. And in this work, we propose something called the Bayesian Stackelberg Markov games, which makes a little bit more assumption than all these three works, but is more general than the Markov games frameworks to capture the uncertainty of attacker types. And naturally, all of these have MDP within them. So we define this new class of games. Then we define what a strong Stackelberg equilibria looks like in these games, and we define a set of properties. Some of the properties, at least lemma 1 and corollary 1, these two can be generalized even from the normal. It's very similar to the normal form game settings, but then this lemma is something that characterizes the strong Stackelberg equilibria in our games. Again, all of these details are there in the thesis, but I won't go into all of these details for the interest of time. Then we propose a new Q-learning, which I call the Bayesian strong Stackelberg Q-learning, which simulates actions in the environment, obtains rewards and the next state, and then solves the Bayesian Stackelberg game formulated by these Q values for each simulation. So as you will understand that this can be costly because you're solving MIQP or an MILP in each step of the game. But if you do that, we show that you are guaranteed to converge to the strong Stackelberg equilibria of this new game. For the experimental results, we develop an open AI gym-like simulator for the three different cybersecurity environments. Well, two, but so one is the web application MTD that we talked about at the start, and the second is the IDS placement and cloud networks MTD that we talked just before this work. And we develop an OpenAI gym simulator. So if any of you want to develop new reinforcement learning algorithms and want to see how effective you are in all of these cybersecurity MTD domains, then I'll put this code up on GitHub as soon as this work gets published somewhere. But if you want it before that, just ping me and I'll be happy to share the code with you. In the experimental results, we compare ourselves to a lot of baselines. The first baseline is the one that we discussed in the Amas paper, which only switches between these two, with the last two configurations for the web applications. So these two cases are for the web applications, and this is for the IDS placement in the cloud setting. And we also use a different set of baselines. One is obviously the URS or the uniform random strategy. We use the Nash Q in the Bayesian Nash Q. And the third baseline that we use is based on a multi-arm adversarial bandit problem adapted to the Markov game framework. But we also needed to adapt that to the Bayesian setting. So we had to modify the code there and adapt it to the incomplete Bayesian setting. And so we use all of these as baselines. And a key takeaway here is that the blue, which is our new multi-agent reinforcement learning Q learning algorithm, outperforms all of these in different domains. Now, this part, which was the AI for MTD part, was mostly finding a theoretical ground and a formal ground such that we can increase the effectiveness of moving target defenses. Now, let's say once we have done that, the question is, can we use moving target defense in new areas and leverage all the theoretical understanding that we gained by modeling this problem in a game theoretic way and finding effective strategies for applying moving target defense to these new domains. And so I'll start off with something that's been extremely popular in the recent years is the adversarial ML, or attacks on neural networks. And for the interests of this presentation, I will only talk about norm-based perturbations, which means you are trying to generate a noise epsilon that, when added to an input image, which was initially, say, of a bus, is converted to this new image, which seems absolutely normal, or this noise seems imperceptible to the humans, but to a neural network, this new input is able to make the neural network misclassify it to an ostrich. And we'll talk about these kind of attacks and defenses for these kind of attacks. An overview of this is available in one of the survey papers that was published in 2019. But then again, the field has also moved on from that, and a lot of newer attacks and defenses have come up. But the basic idea of these defenses for such adversarial attacks from an optimization perspective is that in machine learning, you're trying to minimize a loss function by finding parameters theta such that your input data X has the expected labels Y. Now, when you have attacks, what the attacker is trying to do is it's trying to find a perturbation epsilon such that if that is added to your input, will maximize this loss, which is basically make you misclassify. And the idea of defenses here is that let's do an outer minimization, which says that let us make these attacks, which are these attack input images, and then train our neural network on these attack input images such that you are able to minimize the loss function, not only over the original inputs, but over the adversarial inputs. A key problem that happens is often when you're trying to do this optimization, you might losing out on this one, which is reducing your accuracy on the actual test set in trying to increase your accuracy on the adversarial inputs. And to address this problem to an extent, we look at the notion of moving target defense for neural networks against attacks. The basic idea is that if an attacker crafts an attack that is designed for a particular neural network in your ensemble, but at runtime, so this is randomization at runtime, you select a different neural network to classify it, then it might not, the attacker might not be able to succeed in fooling your network. And a quick question that comes to everybody's mind, given that neural network attacks are known to be transferable, which is basically an attack constructed for one network might work for the other networks as well, is this question of differential immunity. So the characteristic of a differentially immune ensemble says that if you had a single attack that cripples one of the network, it hopefully doesn't cripple the other networks. And we define a formal notion of this transferability of attacks on an ensemble in this work. And the basic thing that you have to get here is that if this value of differential immunity is closer to 1, then there is probably no attack that can cripple multiple defenses in your ensemble. And if it's 0, then there is at least one attack that can cripple all the defenses in your ensemble. And henceforth, using MTD wouldn't really help you. And we take a kind of a shorter route or an easier route in this optimization problem. So the optimization problem here would ideally want you to find parameters of a network that balance between the two objectives of improving accuracy on adversarial examples and improving accuracy on actual examples. What we do is we optimize this objective, but we do it over the probability of selecting a set of networks. So we start with a predefined set of networks theta I, which could be, say, a multi-layer perceptron, a CNN, a hierarchical RNN. And what we want to find is the probability of choosing between these such that you can optimize for both accuracy on adversarial examples and accuracy on actual examples. And if you notice that this optimization problem essentially can be seen as a game. And the idea here is that if you consider each of these theta i's as the defender strategy, and you consider two player types, one is the legitimate user, the other is the green one is the legitimate user, and the blue one is the adversarial user, and you determine rewards of this game in such a way, then basically finding the Stackelberg equilibrium solution of this game will lead you to finding the probabilities for this optimization problem. And so it interleaves very well with the optimization idea of increasing the robustness of classifiers against adversarial attacks into this game theoretic setup and the Stackelberg equilibrium setting for moving target defense. And so having done all that, what is there really advantage to using this? So one part we saw that if we used moving target defense against MNIST, we had an accuracy gain of around 24%. For FMNIST, we had around 22. And for ImageNet, we had 21, which is pretty good given that the state-of-the-art defenses for ImageNet isn't much higher than this. Now, the even bigger advantage of using moving target defense is that you can still use all existing defense mechanisms and on top of it use moving target defense. So basically, we are not really in contest with any of the existing defense mechanisms, but we are a way to complement them. And so the idea here is that if you use ensemble adversarial training for each of the individual networks in your ensemble, and on top of it, use the moving target defense approach, then you could actually get very impressive results, around 51%, around 50%, which is close to the state of the art. And in some cases, I think when we publish this paper, better than the state of the art. We also show that this idea is very effective against black box attacks and attacks that kind of try to learn an approximate function of the entire ensemble as opposed to a single network. I think Dr. Tiffany has a question. Please feel free to ask.
Yes, so I have a question. I have a clarification question when you're talking about the accuracy change when the value of alpha change. So could you give me a brief definition of accuracy at this context?
Right. So the accuracy here is that if you, well, ideally the optimization function uses the loss function value, which says that if you had an input X and the expected label was Y, but you obtain something other than that, then that's the distance function between the actual label Y and the label that you predicted. If the distance is more, then you have a higher loss. And so you want to minimize this loss. And basically minimizing this loss results in accuracy, which would mean that if you have this input example X, then there is higher probability with which you will classify it to the correct class Y. And so the loss function is the stand-in for the accuracy of the network, by which I mean that does it classify it to the correct class or does it not? I have some works recently which look at soft notion. So let's say if you were to classify a particular kind of animal to another particular kind of animal, then it's not as bad as you classifying an animal to an aeroplane. And that's a soft notion of accuracy as opposed to this hard notion of accuracy that's more popular in neural net literature. But yeah.
Yeah, I see. So here, and also here you only think about misclassification, just like a false positive, as long as the tag is not matched.
Right.
And yes, okay. And then here, and accuracy, it's only for like legitimate users. It's not for attackers.
Right, but ideally, if you classify, so you wouldn't know whether an input image belonged to a legitimate user or an adversarial user. And the second thing is, you wouldn't know if you are in some cases misclassifying a legitimate input. And so it's, I mean, ideally what you said is what you would want to do, but there's no way of knowing whether an input is coming from the attacker or the legitimate user. And so you have to try to maximize the accuracy for both and hope that it works out.
Yes. Okay. Yeah. Thank you for the clarification.
Yeah. So we also see how effective is this notion, is this formal notion of differential immunity that we kind of developed for this ensemble. And for now, ignore the third row and consider these three sets. All of these three rows have a 10 class classification problem. And you will see that as the differential immunity of the ensemble increases, the gains obtained by using moving target defense also increases. So basically, the formal notion of differential immunity gives you a nice idea as how the gains provided by a moving target defense systems will help. Why I told you not to consider ImageNet is because this is a 1,000 class classification problem, and henceforth it's not the right way of seeing differential immunity increasing as the gain increasing, because a 20% gain on a 1,000 class classification problem is probably much better than even a 50% gain on a 10 class classification problem. And it's comparing apples to oranges. So I told you to ignore that. But again, we also see that for ImageNet, we also achieve impressive gains by using moving target defense as an add-on defense. Future work would be to consider that instead of only finding the probabilities of selecting the networks, you could consider how could you even make networks that are differentially immune. And maybe you could talk about network compression or sub-network selection at runtime and see if those help. And there is some work which has followed from our work. I have one of them cited here, but there's a lot more that have tried to consider this notion and come up with differentially immune network classifiers or neural networks. Now, having discussed that, I will run through the rest two of the applications, which, as Rao pointed out, got in the last 3 days. And this paper just got in yesterday at GameSec. And the idea here is that for neural networks, it was hard to find neural networks that had differential immunity. But then we asked the question, are there domains where it can be easier to find defense configurations that are differentially immune? And the answer to that question is yes. And one such application is sensor placement in power networks. Now, sensor placement in power networks generally seeks to place the minimum amount of sensors in certain locations of the network or the graph which models the network, such that a unique fingerprinting of the transformers that might incur failures is possible. For example, if you placed your sensors on these 3 points and only this one triggered, then you would know that the failure is in T4. If these 2 triggered and this didn't, then you would know that the failure is in T5. And this is a concept that's been developed earlier. And so the question is, what happens when such a networking system is under adversarial attacks? Because if an adversary can attack one of these sensors, then your unique fingerprinting capabilities go away for all of these 3, and then these 2 become same as T5. So it can disrupt your entire fingerprinting requirement. And in these cases, we propose the idea of using moving target defenses for sensor placement in power networks. An obvious downside is that you would need more sensor placement points, but one good thing is you don't have to place all of the sensors at one go, but you can choose between placing subsets of sensors. And the second is that you get robustness. Now, in this domain, we show that due to the graph theoretic modeling that's available here, we can actually define a concrete problem called the K differentially immune minimum discriminating code set that can actually find you K completely differentially immune configurations or with differential immunity 1. And then we form a quadratically constrained MIQP to solve this. We also show that this is an NP-complete problem. In fact, going beyond that, we show that this notion of a K differentially immune graph solution concept can be generalized to other graph solution concepts. We design some greedy heuristic methods that can solve for an approximate K. Now notice that here there is a way to approximate 2 things, whether you approximate the value of K or whether you approximate the minimum discriminating code sets and you go for discriminating code sets that are not necessarily the tightest possible or the minimum possible discriminating code sets. And we do an approximation for the K here. but a doubly approximation is obviously possible in this domain. And then it comes down to the same theoretical game theory notions that we described till now, where you design the defense strategies for the defender, where they get to place sensors in certain parts of the network. And in this case, the attacker gets to attack one of them. But this attack model or this game theoretic setup could generalize to 2, 3, even more attacks. Obviously not all, because then the attacker would select to attack all, but generally it's assumed to be very costly to attack all power sensor placement points at a single go. And henceforth, you have a particular threat model in this domain. And we show that if you find a strategy using the game theory, which is the strong stackable equilibria, then you're guaranteed to get better gains than using, say, a uniform random strategy. And we also contrast between whether you select the optimal MDCS or an approximate MDCS using the heuristic algorithm. The last work is something that I've done very recently with IBM Research and Dr. Adam Dupe on bringing the notion of proactive or moving target defense to cyber deceptions, and in particular, honey patches. Now, to give you a first-hand overview of what honey patches are, is basically, let's say you have a code which is vulnerable in the if condition. A patch for this piece of code would be essentially putting a stricter if condition that handles the case because of which this was vulnerable. And an even better way of doing this is you handle the condition, but if the attacker still can exploit this, then instead of reporting error, you actually fork a process that imitates your real system and makes it look to the attacker as if they have access to the actual system, but you learn the attacker's behavior on what they're going to do. Now, in deploying honey patches over a longer period of time, there are certain downsides to it. The first obvious one is that an attacker has reconnaissance time, and they will eventually figure out which vulnerabilities are actually honeypots and basically not choose to exploit them. The second is the attacker can also spend time, given enough time, figuring out a vulnerability in the honeypots and then actually attack your system. And so a way of addressing some of these is to consider this notion of moving honeypatch deployment. And what this does is basically you are shifting which places you have honey patches deployed in, and henceforth the attacker can never be sure that if the attack they are using against your system is actually going to give out more information about them, or are they actually really getting access to your system's data. Now, a notion that is very important in these settings is that when you're deploying a particular code version in prod, which is going to be your defender strategy, they have to be conflict-free, which means that you cannot have two different patches that are going to change the same line of code and expect that that code is a possible configuration that you can deploy. And to address this, this notion of conflict-freeness and only come up with defender strategies that are conflict-free, we have an algorithm. But the trickiest part of the algorithm is that using a version control system like Git doesn't really help you as much, because in this case, you have to pull pairs of patches to see if they conflict between one another, and they have to respect certain dependency constraints. And if they don't, you have to obliterate them. And these obliterations can be much more difficult and rather much more mathematical than what we do in version control systems like Git or so. And so to address this problem, we use something known as DARCS, which is a version control system that uses patch theory. It supports inversions of patches, commutation of patches, particular ways of cherry picking, and obliteration of patches, provided that it respects certain patch consistency constraints. And using DARCS, we can easily find the different configurations that the defender can use to deploy a particular piece of code on the production server. Then again, as I've been talking about throughout this talk, once we obtain the conflict-free patches, we can obtain some threat intelligence data from, say, CVE, CVSS, and then use both of these to figure out a game theoretic strategy for the defender, and then choose a version patch deployment using moving target defense in such a system. And by doing this, we show that in existing methods where honey patch is basically static, which is you deploy the best honey patch that you think is going to be the most effective. In the long run, it gives you a much lower utility. The up arrow indicates the higher value is better. And since these are negatives, a negative magnitude would indicate that this is the worst of. If you use something like URS, then you will actually land up using many more honey patches than you probably require to get uh, a secure deployment of your moving target honey patching. And if you use the game theoretic strategy, you get the best gains, and you also reduce the number of patches that you need to deploy on your production code. So with this thing, I complete talking about all the different works that I have done. But a notion to keep in mind is this distinction between model-based, model-free, and even model learning is something that I don't address. Now, in all of these works, which is these three and these two, I have talked about how you can obtain a model given some of the databases, attacks that is readily available. And once you have that, how do you design mathematical and formalisms and mathematical techniques that can solve for the strategy in these models? Now, the question is, when such a model is not available, or even if it's incorrect, then you can start with a strategy that you inferred and then use a model-free approach to improve your strategy, or even learn a strategy from the very start. And this distinction becomes quite important, but this is something that I've started looking at in the very recent years. Besides this, I have an overarching framework for moving to target defense in general. To show you how general this framework is, I've also incorporated the new works that I did on the application side of things into this formalism of what the defense moves, what is the timing function they use, and also made an extra categorization in the thesis on how to move. So basically, my works before this was mostly concentrated on single stage and multi-stage, but considered strategy inference. But now we also consider the aspect of strategy learning. And I talk about some of the existing works there and the new work that I've done. We also discuss a lot more detail, in a lot more detail, how some of these MTDs are implemented in network scenarios and how are their effectiveness measured. And this is a paper that is appearing in IEEE Communication Surveys and Tutorial this year. Besides this, I think Rao has already pointed it out, but I have had a much bigger hierarchy of things that I've been working in. I'm mostly interested in multi-agent systems, and I have looked at the adversarial or non-cooperative side of things. And this thesis constitutes of my work in the area of cybersecurity and multi-agent modeling. But I have also worked with some of the lab juniors on game theoretic trust, and on the cooperative side in cases where sometimes the machine has more knowledge than the human it's interacting with. Sometimes when the human has more knowledge than the machine it's interacting with, and the assistant scenarios. I think somebody wrote something in chat. Okay, sorry. Yeah, they just said they joined, so that's okay. And in the middle lies this notion of assistance, where both of them are trying to help each other in achieving an objective. And I have also some works on heuristic search and planning, natural language processing, generative adversarial networks, and even data set generation, which is not here. I'm presenting a much larger overview of this work tomorrow at the MSR AI Breakthroughs, where I was invited to give a talk. And okay. Over the years of my PhD, I have accumulated around 186 citations, at least as per yesterday. And the survey that I wrote this year has already received around 10 citations. So I'm hoping that people find it actually useful. And I have also a set of code bases that I've made available that really doesn't need you to understand all the mathematical modeling, but provide inputs of your MTD system in a particular format, and you can just use these inference codes to find out what's the best strategy for your setting. Besides this, I have been nominated and won the IBM PhD Fellowship in 2018. I got nominated for giving an invited talk at the Microsoft Research AI Breakthroughs. I have been voted as the top 3 intern projects. My project has been voted as one of the top 3 intern projects during my stint at Amazon Research in 2019. And my work on incorporating game theoretic modeling for cybersecurity has been featured as a hot trend in AMAS 2018. I wish I could say that all of this is my own work and I have been able to do all of this by myself, but that's not the case. I'm thankful to a huge amount of people that have collaborated with me, helped me understand things, especially Rao, who has been a mentor, who has found the perfect balance in hand-holding me at times and giving me critical feedback and saying that my idea is never going to work. And in both of these, in how he's acted as an adversary or a critique in criticizing my ideas and giving constructive feedback and hand-holding me in writing papers, identifying incorrect assumptions, incorrect things in proofs. I think I owe it to him mostly. Besides that, I've been fortunate enough to work with a lot of the SIDSI faculties at ASU. I'm a little displeased that I haven't actually worked with Dr. Tiffany Bao and Guliang Shui, who both have worked on optimization, and Dr. Tiffany, like me, also believes in the philosophy that using formal modeling and game theoretic ideas can really help in boosting the effectiveness of cyber defenses as such. But yeah, I guess we cross roads in the future. I'm thankful to a set of people from IBM Research who have collaborated with me and invited me to give invited talks and attend some of their workshops. A set of people at Amazon Research with whom I've also worked, and they have helped me grow as a researcher. And a huge number of people, obviously, in the Yochan lab, in Dr. Dijan Huang's lab, in Dr. Arun Abasen's lab, with Dr. Adam Dupe, and all of them. So a big thank you to all of these people. If you are here on the call, again, thank you from the bottom of my heart. Now, a conclusion or a takeaway for this talk is basically, if you are considering a security setting, consider using movement strategies. Consider using moving target defense. If you don't, as Xu Zhu says in The Art of War, strategy without movement is the slowest route to victory. And you can obviously do better by incorporating moving target defense as an add-on defense. So you will lose nothing by using your already existing security, but probably gain more by using moving target defense. And if you're choosing to do so, ask yourself 2 questions. Can the defense strategies for the moving target defense be easily constructed? If not, if it's really difficult to do that, then probably you won't be able to use MTD. The second is, does constructing this help you? Because if you have multiple defenses and all of them have an Achilles heel that they're vulnerable to, it doesn't really help. But if there is something that one configuration gives that the others don't, then you are probably better off using MTD, and you will see significant gains in security by simply using MTD with your existing defenses for this security domain. The second is, if you are planning to use MTD, then do it in a clever way. Model it as a strategic multi-agent interaction. If there is enough data available for you to construct this model by mining from these databases, then use one of the inference mechanisms. I have links to the code that you can just go and use it if you're modeling it as a normal form game or as a Markov game. And if you think that these modeling parameters cannot be readily available, but there is some way you could either design a simulator or even have an interaction with the real system, then use something like multi-agent RL and find equilibriums, and I have a code base for that as well. With that, I will conclude the talk, and thank you to everybody for listening in. Over to Rao.
Okay, great, thanks, Sailik. So right now, yeah, I know we really should be doing some way of clapping. So imagine large number of claps, Sailik, please, if you may. So right now we have the open part of the question answer session where anybody in attendance, including of course the committee members, can ask any questions they have. If you want to ask, just unmute yourself and ask a question,
Please go ahead.
So maybe I can start.
Okay, go ahead.
Yeah. So just based on look at the collaboration slides, I can see your bright future, right? So this is good to see you have been working with so many people. So at this stage, that's wonderful. Just have one technical, not in-depth question, just like on the surface still. When you talk about the moving target defense and using the game-based strategic models, we know people have different opinion regarding to how to deal with potential vulnerabilities, right? So some people may say, okay, we may rely on the attack graph, right? So to see how we plan out the countermeasure or maybe mitigation strategies. Some ones may say, okay, so we may just block it or stop it or shut it off, right? So this is all kinds of strategies out there, right? So how do you handle this variety of number of different ways? How you make the model is more adaptive instead of statically based on predefined strategies to do the countermeasures?
So one of the things we are recently looking at, and this is with Dr. Adam Dupe and some of the IBM folks, is that we are trying to say that what strategies are actually going to be effective in capture the flag tournaments. Because even in capture the flag tournaments, when you say, and I think this is some work that Dr. Bao has also looked into, which is basically, should you patch a vulnerability? Should you not patch it? Should you just drop the package? Should you redirect them to a honeypot setting? Should you just not do anything and just let them anyways use the attack because the scoring system won't affect it? And the idea is that if you could formally model each of these actions as a defender's action, even if you can't get the values for the reward functions, but you could interact with such a CTF environment, you could learn what is a good strategy that will yield you the highest rewards. If you could get the model that gives you the rewards and the transitions that will take you to other states, then you could infer good movement strategies for the defender as well. And so the idea is that just by modeling this as a multi-agent interaction and a more precise notion of a game, then you will be able to say what strategies are strictly going to be better than any existing strategy, such as say dropping the packets, or say just let's deploy a honeypot, or say let's let the attacker go, we'll exploit more attacks and stuff like those. And so we are looking at some of these questions, I guess not maybe in as general the aspect that you're pointing out, but some of these questions in the CTF framework. Okay,
yeah, just a follow-up. So if you say there's a multi-step, multi-agent based decision model, so how this can emulate the human's activity? So, or from another side, we can ask how important to mimic the human's action from a machine aspect. So do you think that is important, or is just not important? So
no, right. So I think, yeah, I'll be honest about that part, is that in most of these game theory works that I've considered, and I think this is something that Dr. Shuey had brought up during the proposal as well, which is all of these kind of assume a rational adversary, and often cyber attackers might not be rational. And in those cases, there are kind of two ways to do this. One is you have a formal definition of a bounded adversary, where you say that the attacker can play an attack which is not the most optimal, but within some range of the optimal and stuff like those. Or the other way is that you could actually deploy certain systems and see what the attackers do on those systems and learn an approximate model for the adversary, and then use this again multi-agent setting to find good defender strategies. So that is something that I've also discussed with Ankur and even Dr. Dupe at some points in time about doing it, but that hasn't happened throughout the PhD, but probably that's a very interesting line for future work.
Okay, great. Thank you.
Hi, can I go next?
Yeah, go ahead.
Hey, Sailik, thanks for the talk. Most of the stuff that you talked about was totally beyond what I know, but the great thing was I wasn't bored at all. In fact, I was totally engaged. So it was a great introductory talk for me in some of these areas. So one area that I do know something about is neural network defenses and adversarial attacks there. So unfortunately, a lot of work has been focused on LP norm perturbations, as you talked about, right? So perturbations in images that can be that are essentially inside a LP ball. So it's, as you said, it's a noise.
Norm-based perturbations, yeah.
So does your formulation allow for any other types of perturbations? And if so, do you have any results on that? Because I know that in the image, like vision domain, no one is really exploring these.
Right. So that's a very good question. And I actually have an entire supplementary appendix section in my thesis devoted to this part, but let me address that. So when you talk about things like adversarial patches, which is sort of real world attacks that you can use against a neural network system, the problem is this neat framework of fitting the optimization as a game doesn't really work. But if you consider it at the level of an ensemble where you're using different networks and say a particular network is immune to adversarial patches, which are say box patches. Some adversarial networks are immune to patches, which are say images of animals and things like that. Whatever you have beyond norm-based perturbations that are more realistic attacks, then you could club all of these together in an ensemble and still consider MTD. And the kind of model or metric values or statistics that we use to calculate the rewards of the game are simply accuracy values. So at that point, you don't have to really care about, can you give any theoretical guarantees about where the optimization would converge for these kind of new attacks? You don't. You just have to calculate the accuracy values on an adversarial test set and just have these values populate the rewards of the game, and you could still find the strategy. So the answer is yes, the MTD framework still works out of the box, even for non-adversarially perturbed adversarial inputs. But at the same time, the clean distinction of how we relate the game to the optimization setting, that distinction is a little merged or blurry.
Right. Okay. And you also hinted at learning the parameters themselves while you're training this moving target defense.
So yeah, actually, let me go to this.
In a neural network setting, could you explain how that would probably work?
Yeah, I will. So there are two things you can learn and one thing you can do. So one thing is you can obtain the model from existing databases and use a strategy to infer. The second thing is you could learn two things, whether you could learn a model and then use strategy inference, or you could choose to skip learning the model and just directly learn the strategy. So this work kind of talks about skipping learning the model, but just directly inferring the strategy. So this could actually work out for all of these defenses as well. So ideally for your case, and this is something that I've thought about because it's like this very first order idea that you come to having seen this slide, is that if you use a neural network and you design a single patch and you choose a particular neural network configuration and you provide both of them, you see what the environment returns. Does the neural network get fooled? Does it not get fooled? You give a +1, -1 reward, and you use a reinforcement learning approach that I talked about, and you will simply be able to learn a good strategy. A bigger thought that I have is that instead of only learning the strategy, which is the p-value, could you also learn some novel neural network parameters? So could you incorporate this entire reinforcement learning paradigm as a backprop algorithm such that you not only learn the probabilities over these networks, but you actually land up learning a set of networks together that will provide you some kind of robustness towards adversarial attack? So that's a very good question though, yeah.
Okay, thanks a lot, Sailik.
Other question? Go ahead.
Yes, hi, Sailik. First of all, this is a great talk, and also everything is well organized, and you definitely have covered a lot of content that you have done during your PhD, which is amazing. So I have a question. Yeah, I have a question in terms of the cyber deception part that you just talked about. So my question is that, first of all, let me just make sure that I understand that correctly. So in this MTD model, the defender will decide the strategy of which place to patch, and right, like whether or not the defender wants to apply a honey patch. So there's two possible action space. One is honey patch and the other is no honey patch, which implicitly means patch, just like a true patch. Did I understand that correct? Like, right. So it's like either patch or honey patch.
Right. So ideally, that's a very good question. And let me actually point that out. Maybe I have written it somewhere. Okay. Yeah. So the point is, okay. So at least I talk about both the notions of using honey patches or just patches, which are normal patching the vulnerability. And the idea is that if you have a possible code base that in which some of these are honey patches, I think this is too small, but then P3, there is a honey patch. P3 also has a normal patch. And you want to select, so basically you're going to select a subset of which some vulnerabilities are patched and some vulnerabilities are honey patched.
Yes, so there's no vulnerability that are not patched, right? So for all of them, they will be either patched or honey patched.
Right. So So in fact, a very interesting notion that comes up is that in the first work when I was talking about, I talked about this.
Yes, there's a case that there's no monitoring, right?
Right. No. This is the web application case where there was no real incentive for the defender to get a positive reward. But if the attacker exploited something in one of their configurations, they could rather get a negative one. In the case of the honey patch, the thing is a little of a reverse because there is no chance that the defender would anyways be affected because you will at least have it patched or you're talking about a honey patch. And the question is how much can you gain on the positive side, which is how much of the attacker can you know about by deploying a particular honey patch configuration. So it's kind of a exact complement or rather a supplement maybe of both the works. So
yes, I see. Interesting. Yeah. So then following this question, I would like to know that, if the MTD strategy has been, calculated and implemented, and then attacker may be able to observe the strategy. So then this game turns to be a stackable security game.
Right.
So can you follow this thought and think about what will happen if we follow by this MTD game, it becomes a stackable security game, what will happen? And how we can, deal with it.
Oh, okay. So ideally, all of the work already understands that. So it already considers the Stackleberg setting where we have deployed the MTD. The attacker gets to know your configuration or the strategy, and henceforth you're finding the Stackleberg equilibrium, which is close to Stackleberg security games, which is the initial optimization problem that I pointed out. This is by Dr. Thambe's group, and this is by Dr. Konitzer's group. And they kind of design these for the Stackleberg security games. But then we talk about interesting challenges that arise for switching cost in cybersecurity that they never incorporated, and how to account for those, you have to come up with newer techniques. In the second case, we also land up using some of these Stackleberg equilibrium solvers, but in the context of Markov games. And in the third case, we also land up using the Bayesian Stackleberg game solvers, but more in the context of learning and converging to an equilibrium. So yes, so it's very closely related to Stackleberg security games to answer that question, but it also already models that the attacker might have that stronger threat model where they know about the defender strategy.
I see. Yeah, this is good to know. And another question is that, what if attackers, by playing this game for many times, or say they're attackers, they're collaborative. So if there's 1,000 attackers and each of them just play this game for a time, and then they will be able to enumerate all the possible honey patches. And then in this case, attackers will know that those are the vulnerabilities that may not be honey patched, so that they will just play their, in the most conservative way, not attack any of those vulnerabilities and then decide to attack other vulnerabilities. So in this case, can you, or is there a way to give a mathematical approximation of, if someone is going to play this for many times, approximately by how many times this MTD may expire? The strategy may not play into an fact.
Right. Okay, so that's a question I have been kind of looking into, but it isn't that easy a question, which is the question of what is the sample complexity for converging. So I've been looking at it from the other side, which is what is the sample complexity of converging to an optimal strategy. But I think what you're asking is that what is the sample complexity for the attacker finding out your model and then converging to a strategy such that it can always exploit your system. Now the assumption that we have made even in the cyber deception scenario is that even if the attacker has one particular attack that can cripple all your defenses, which is basically gives you no differential immunity. So all of these defenses that you're playing has at least one vulnerability that the attacker can always attack, and not just attack any of the others because honey patches don't exist for that particular vulnerability. Then that's already a gone case, because then the attacker can only keep on exploiting that vulnerability and just getting their own rewards. So that is anyways a lost case. At that point, even the notion of honey patch deployment wouldn't make sense. For example, you have honey patches against 10 code vulnerabilities and you deploy them, and the attacker exploits an 11th one. At that point, whether you use an MTD or you don't doesn't really matter. So the question is, again, I think the question is absolutely relevant, but I think that question also goes on to any normal defense scenarios, even that doesn't use MTD. For MTD, all I can say is that it will take more time, but I don't have sample complexity results by when the attacker can figure that out. Yeah.
Yep. Gotcha. Thank you.
Yep.
Other questions? Other questions from the audience other than the committee members? Going once, going twice. Okay, so if the attendees don't have any questions, at this point, I would request that they drop off the line, just drop off yourselves, and then the committee would still continue to